Hello students, I'm going to review the last section of the reaction mechanism notes. Okay, so it's on addition. There are two types of addition which you need to know for H3 curriculum, as well as H2 of course, electrophilic addition and nucleophilic addition. Okay, so for electrophilic addition, it's not very different from what you have learned in H2. Yep. And for the purpose of the current H3 curriculum, you do not need to know any new mechanism pertaining to electrophilic addition to alkenes. Yeah, unlike the old H3 curriculum where we specifically teach you the electrophilic addition of alkenes with bromine via this particular intermediate. We call it the cyclic bromonium intermediate. Yeah, so let me just emphasize that this is not required for the current H3 curriculum, but it's something we just want to add on a little bit for your enrichment. Yeah, and if you are interested, you can actually pause the video for a moment and then move on to work on activity 5. Yeah, so activity 5 was given to you in the tutorial last week, but we did not go through it because it's meant for everyone as an enrichment to work at home. Yeah, it's on the stereospecific addition to alkenes with bromine and chlorine. Yeah, so if you have not done activity 5, it will be good to do activity 5 before you review the current section, because if not, then the bulk of the review will already tell you most of the answers to activity 5. Yeah, but if you have done it, then yep, it's fine. So you can just go through the section as a form of review to what you have done. Okay, so basically the difference between the electrophilic addition of alkenes, or rather of HBr and bromine to alkenes, right? The only difference is that when you are adding bromine or chlorine, it goes through a cyclic bromonium intermediate, which look like this. And because the cyclic bromonium intermediate is locked at the top phase, and this first step is actually the slow step. Okay, so this first step is the slow step. So in the fast step, the bromide anion can approach from either carbon 1 or carbon 2 from the rear. Yeah, so it's very similar to the tutorial question 3 which you have done, where for the tutorial question 3, the hydroxide anion approaches from the rear of the CO bond in the epoxide, which facilitates its ring opening. Yeah, so it's the similar case for cyclic bromonium. Yeah, so it actually approaches from the rear of the CBr bond, and in the process the ring opens up, and then you notice that the Br is now found here, and then the other Br is found here. Yeah, so if you try to draw the mechanism with another bromide approaching from carbon number 1 and the ring opens up, yeah, you are going to draw another molecule out, and you notice that for the case of trans-but2-ene, you are getting the same compound, which is what we call the meso compound. Okay, it is impossible for you to get the other pair of stereoisomers. The reason is because the bromide cannot approach from here or here. Yeah, remember that for the ring opening to take place, it is similar to an SN2-like fashion. So that means that it has to approach from the rear in order for the ring to open. And why is rear attack an important aspect here? I think after you have learned MO, molecular orbital theory, you'll recognize that when SN2 kind of reaction takes place, the nucleophile approaches from the rear of the C halogen bond. The reason is because the rear is where the sigma star anti-bonding orbital is pointing. Yeah, so that is when you introduce electron density to the sigma star, and because of that, so-called the bond breaks, and then a new bond is being formed between the nucleophile and the carbon, and then when the bond breaks, then the other CBr bond results. Okay, so I don't want to go into too much detail, so I guess you might just want to read a little bit about it over here. Some students will ask whether the cyclic bromonium has been established. My answer to you would be yes. The cyclic bromonium cation has been isolated using experimental means. Yeah, but the isolation usually involved the scientists or the chemists introducing very bulky groups over here. So when we introduce very bulky groups, it's preventing nucleophilic attack from the rear. So the groups are so bulky that the rear is kind of blocked because the the groups will kind of point downwards. Yeah. And some students will also ask, why isn't a carbo-cation intermediate formed instead? Well, the cyclic bromonium intermediate has its advantage because all atoms has except hydrogen, of course, has the octet configuration. Yeah. The drawback of a carbo-cation is that the carbocationic center is electron deficient because it only has 6 electrons around it. Yeah, but if we have a cyclic bromonium, you notice that all non-hydrogen atoms, right, have the octet configuration. So it kind of like give the system an added stability. Yeah, so that is something scientists realize. So of course, it's not something which you have learned in H2 and not in current H3 curriculum, but it doesn't really matter. So if you read out on some introductory organic chemistry books, you will definitely encounter a cyclic bromonium. But it is only for bromine and to some extent chlorine, not for iodine, not for fluorine. Okay, so most of the examples you have encountered will be for bromine, in fact. Okay, so over here we have the mechanism for the electrophilic addition of cis-butyl-2-ene and trans-butyl-2-ene. This is probably the answer to your guided inquiry or to your activity 5, the stereospecific addition. Yeah, so for cis-butyl-2-ene, I'm going to get an enantiomeric pair. And for trans-butyl-2-ene, as what you have seen earlier on, you are going to get a meso compound because these two are actually the same molecule. Yeah, so if you look at them carefully and you draw them out there, you are able to draw an internal mirror plane. Okay, yeah, but please do not stretch this idea too far because the addition of halogen, HX, right, it is still a normal electrophilic addition where you generate a carbo-cation. Yeah, because this has no choice. Why no choice? Because H cannot form additional bond with the other carbon, right? It's because H, as long as it has the duplet configuration, it is already stabilized. Yeah, it is what we call the closed shell configuration. Yeah. Okay, so and that is probably the reason why in order not to mess up too much with the students conceptual understanding or add too much to your academic load, that is why the electrophilic addition of bromine, specifically the formation of the cyclic bromonium intermediate, is being taken out from the H3 curriculum. Yeah, so as to reduce the workload of the students and in some sense to reduce your stress. Yeah, and I think you have seen this particular term stereospecific, okay, which we have sort of discussed with you a little bit in the earlier lecture. So basically, stereospecific reactions are reactions where they are controlled by the nature of the mechanism. Yeah, so that means that when we actually when we form this particular cyclic bromonium intermediate, right, it is impossible for me to result in the other two products. The reason why you can't form the other two products is because the bromide anion has to approach from the rear of the CBr. Yeah, so the bromide cannot approach from here. If it approach from here, of course, I will be able to get a randomized mixture of products. Yeah, and this is also how scientists uncovered the cyclic bromonium intermediate. Yeah, because they noticed that when I start off with cis-butyl-2-ene, I only get one enantiomeric pair. Trans-butyl-2-ene, I getting the meso compound, and there is no scrambling of the products. Yeah, so because of that, they suspect that the mechanism do not undergo reaction via a carbocationic intermediate. Yeah. Okay, so that is one experimental clues which showcase and tell scientists that, you know, it's not possible for any other mechanism to take place. Of course, it's possible if there are new things being uncovered, but at this stage, no. Okay, yeah, so I'm just going to move on because this particular portion, as I mentioned, is not exactly in your curriculum, so we don't want to spend too much time on it. We have an exercise 4 where we were told that the bromine, when it's reacted with separate samples of malic and fumaric acids, one acid produces the pure meso compound and the other produces the racemic mixture. So which acid produces which? Explain your answer. Yeah, if you really scrutinize this particular cis and trans so-called malic acid, right? Or rather, malic acid is the cis version of the dicarboxylic acid, and fumaric acid is a trans version. I think you can straight away tell that you can easily map it into whatever we have over here, the cis built 2-in and the trans built 2-in. Yeah, take note that these two are the same functional group, or rather the same group being bonded, which is methyl group. Okay, it's not written for you there because it is obvious that if nothing is written there, then there should be a carbon, and therefore it's a CH3 lah. Yeah, so therefore I can conclude that fumaric acid, which is the trans version, will give me the meso compound. Okay, I do not really need to draw the mechanism out for you because again, I mentioned it is not in your curriculum. So if you want to verify it for yourself, please verify that for fumaric acid, it's the one which gives us the meso compound. Okay, then for malic acid, it's the one which gives us the RR 2,3-dibromo butane dioic acid and the SS 2,3-dibromo butane dioic acids. Yeah, so please verify it for yourself, and if you are interested, draw the mechanism and give yourself a little bit more practice. Okay, so with that, let us take a look at nucleophilic addition, which is actually for your H2 is topic 17. So you might want to review topic 17 first before you move on to this particular portion of the notes. But it's actually okay if you just read through a so-called abridged version so that you have some ideas on what exactly is happening for nucleophilic addition. And if you have gone through, and of course we did go through some parts of our mechanism activity 6, then you will be introduced to this particular functional group known as the carbonyl, the C double bond O. Yeah, so it is polarized, so the carbon gains a partial positive permanent charge, the oxygen a partial negative permanent charge. And because of the polarization, the carbonyl carbon is susceptible to nucleophilic attack. Yeah, and if I may just stretch you a little bit by showcasing a little bit of MO to you, right? For the pi bond, the CO pi bond, for the bonding molecular orbital, we have two of the pi bond with the same shade here. So what you're going to get is what was shown in this green portion. So meaning that I'm going to get the bonding molecular orbital to have the top with one face and the bottom another face. Okay, but for the anti-bonding, so this is pi. Okay, for the anti-bonding pi star, right, it actually looks like this. So it's here and here and here is and here. Yeah, so anti-bonding is formed from what we call destructive interference. Yeah, so what exactly is constructive and destructive interference? Those of you who have taken physics, I think it will be clearer to you. Yeah, so basically a p orbital has two regions, the positive phase and the negative phase. So if you represent the positive phase with a shaded bubble, and then when two positive phase interact, they result in what we call a constructive interference. Yeah, so negative phase both interact, it also result in this. Yeah, but sometimes when orbitals overlap, right, they can overlap in two fashion. One is constructive overlaps, and the other will be a destructive overlap. Yeah, so anti-bonding pi star, sometimes we call it the evil twin. So when they interact in this particular fashion, right, then you result in this particular anti-bonding pi star orbital. Yeah, and you notice that the anti-bonding pi star orbital, right, if I just use an orange ink, it's pointing at about 109.5 degrees from the horizontal. And true enough, right, when nucleophile attack the carbonyl carbon, it approaches 109.5 degrees from the CO plane. Yeah, so it's making 109.5 degrees angle of approach. Yeah, it is not a vertical approach. Yeah, contrary to popular belief, it does not approach it vertically, or it doesn't approach it from the rear. Okay, so the approach is either 109.5 from here or 109.5 from here. Yeah, and that will explain to you certain things later on which you will encounter. Yeah, so but of course for the purpose of H2 and even for H3, right, when you draw the mechanism, you do not really need to show the 109.5 degrees angle attack. Yeah, when you draw your arrows, you can simply just draw it looking as though it's approaching from the top. Okay, so it doesn't really matter here. So that is not something we want to add to your worry. Okay, so for example, for nucleophilic addition of HCN, which you are going to encounter in H2, yeah, so the cyanide approaches. Okay, my apologies for this weird fat-looking arrows, but yeah. So basically, the cyanide approaches like this, and then now the bond breaks towards the oxygen to give you a tetrahedral alkoxide intermediate. And the tetrahedral alkoxide intermediate will then attack the hydrogen here, and then the bond will break towards the cyanide. Okay, and of course the carbon is the one bearing the negative charge, not the nitrogen. So do remember this. Yeah. And I think it's quite obvious from the bonds being formed. So the bonds is being formed between carbon and carbon. Okay, so yeah, so it's the carbon which approaches the carbonyl carbon, not the other way around. Okay, yeah. So the rate determining step is the first step, where you produce a tetrahedral alkoxide intermediate, which is unstable, and then the fast step is the protonation step. I think we have talked about this in our activity 6, so most of you should be quite familiar. Okay, the rest of the details you can actually get from your H2 notes. And for the nucleophilic addition onto the carbonyl carbon, the attack is also from two phase, the top and bottom phase. You might notice that when we draw out the mechanism like this, right, it seems to approach in a 90-degree angle. Yeah, but remember that when we draw arrows, right, when we do arrow pushing, it's basically just a representation. It doesn't represent the actual angle attack. So the actual attack is actually from this particular angle. Okay, it's 109.5, either top or bottom. Yep. Okay, so and you might also be able to recognize from what we discussed on attack from the two phase that the nucleophilic addition will also give you a racemic mixture. Yeah, but the difference between this mechanism and electrophilic addition, right, is that for nucleophilic addition, when the nucleophile approaches the carbonyl carbon from the top and bottom plane with near equal probability, you start by generating what we call a racemic intermediate. Okay, so the intermediate is already a racemic mixture. That is the largest difference. Remember this. So the intermediate is already racemic. Then the protonation obviously will result in a racemic mixture. Yeah, but for the electrophilic addition of let's say HBr to an asymmetric alkene, you generate a carbocation which is trigonal planar about the carbon bearing the positive charge. Okay, then after that, the nucleophile approaches it from the top and bottom plane with near equal probability to give you the racemic product mixture. So there is a difference. Yeah, okay, so for the nucleophilic addition, you generate racemic intermediate followed by protonation. But for electrophilic addition, or for that matter SN1, where it goes through a trigonal planar carbocation intermediate, right? The carbocation intermediate is the one with the trigonal planar geometry about the carbon bearing the positive charge, where it's being approached from the top and bottom plane with near equal probability by the nucleophile. So there is a difference when you are discussing. Yeah, I mean, I'm saying this because sometimes in exams, right, they need you to discuss what's the difference between nucleophilic addition and electrophilic addition. Yeah, why is there really such a difference? And as I mentioned earlier on, whether a reaction is called nucleophilic addition or electrophilic addition is really based on the perspective, and there is some legacy issue behind it. Yeah, so for nucleophilic addition or electrophilic addition, or for most organic chemistry mechanism, yeah, the legacy issue is when we tend to name mechanism based on the non-organic substrates. Yeah, so for nucleophilic addition, you notice that the nucleophile tends to be non-organic, and then the substrate is organic, right? So what does the non-organic thing, or one non-organic species, what does it do to the organic substrate? Yeah, so in this case, nucleophilic addition, because my nucleophile is the one which approach the organic electron deficient sites at the carbon. Then electrophilic addition of alkenes onto, let's say, HBr is when the organic substrate is the alkene, and then the inorganic substrate is the one which has an electron deficient site somewhere. Yeah, so that is the difference. Do take note of some of these legacy issue which exist in chemistry. And some of you might remember from what I mentioned either last year or during tutorials or even the online lectures that a lot of these legacy issue can be solved or has already been solved by IUPAC, but it is just that it is very difficult to implement the renaming of the mechanism. Yeah, it's very difficult because most of us, we learn it in a particular manner. So because we learn it in a particular manner, we tend to teach it in a particular manner as well, and it's a lot of things is very difficult to change. Okay, yeah. So with that, we're going to just move on to the next portion on nucleophilic addition of alcohols. The alcohols act as nucleophiles to add on to the carbonyl compounds. If 1 mole of alcohol is added to an aldehyde, you get something known as hemiacetal. When 1 mole of alcohol is added to the ketones, it's known as a hemiketal. Okay, then when 2 moles of alcohol is being added, what you get is an acetal, and 2 moles of alcohols being added, you get ketal. Okay, so I'm going to show you the mechanism over here. Yeah. Some of you might wonder, right? Why is it that the carbonyl oxygen must be protonated first? The reason is this. Number one, right? The alcohol is a poor nucleophile. It's not very electron rich at the oxygen, although it looks like it is. I mean, the carbonyl carbon is also not as electron deficient as it makes out to be, unless it is being attacked by a strong nucleophile. Yeah, so if we want the nucleophilic attack to go faster, there are 2 things we can do. Either we use a stronger nucleophile, so in this case we can use alkoxide, that means RO minus, or we can make the carbonyl oxygen more electron withdrawing by protonating it with the relevant H plus or other kind of Lewis acids. Yeah, so in our case here, the protonation of carbonyl oxygen with H plus is used, so that is why it's called acid catalyzed. Yeah, and because of that, after protonating with the H plus, the carbonyl oxygen is now more electron deficient. So the increase, or rather the carbonyl oxygen is now more electron withdrawing. So the increase in electron withdrawing ability, right, will make the carbonyl carbon more electron deficient. So therefore, it is now susceptible to nucleophilic attack by a poor nucleophile such as ROH. Yeah, so in this case, the poor nucleophile now can attack it. And now, after the nucleophilic attack, the ROH, the oxygen will gain a +1 formal charge, and then now a proton is lost, and we are getting this compound known as a hemiacetal. Okay, sorry, this is hemiketal. Yeah, because we started off with a ketone. Okay, so we need to remember that we start off with a ketone. So what we are getting here is a hemiketal. Then if you are wondering, if this continue, how do we get a ketal? Okay, so what is likely to happen is that remember that earlier on it loses a H plus, right? Okay, so now the H plus can also be gained by either the oxygen, either of the oxygen. Okay, if it gains by the other oxygen, you're going to get back this lah. So if it gains by the hydroxyl oxygen, then I'm going to end up with something like this. Okay, so I'm just going to draw it out. R carbon, R1, and then O, and then R1, and then OH2 plus. Yeah, so now the oxygen is made a good leaving group. Yeah, so because of that, now the pi bond between carbon and oxygen will be formed, and in the process I'm going to kick out H2O. Okay, so once I kick out H2O, it's going to be an equilibrium reaction as well. Yeah, I'm going to end up with a compound which looks something like this, with a carbon here. I'm just going to draw the carbonyl carbon, and then with a double bond, O, and then R1, and this O will take on a +1 formal charged. Okay, and this can continue with the alcohol lone pair performing a nucleophilic attack on the carbonyl carbon, and then now the pi bond breaks towards the oxygen. Okay, so if you are sharp enough, you are probably going to recognize that I'm going to get something like this, O, and then R1, and then now I'm going to have it's a O, H, and then with a plus, and then R1 as well. And then this H will be lost, and eventually I'm going to end up with what we call a ketal. Okay, so I'm just going to draw it here. So the ketal looks like this: carbon, R prime, and then O, R1, and then O, R1. Okay, so this is known as a ketal. And all this, right, they are all equilibrium processes. Yeah, so potentially if I change, I can just adjust the condition such that I can favor one over the other. Yeah, this is a very popular a way of what we call protecting a carbonyl group. Yeah, so what do we mean by protecting the carbonyl group? You notice that once I form the hemiketal or the ketal, right? Okay, so this is called ketal. Once I form them, the carbonyl carbon is no longer present, so there's no more pi bond. Yeah, so in that case, it will not be able to undergo the usual nucleophilic kind of addition, or later on you're going to learn addition-elimination kind of processes. Yeah, so it's like protecting the carbonyl group from being attacked unnecessarily by nucleophiles. Okay, yeah. So if you're interested, you might want to read on regarding the nucleophilic addition of alcohols. So this series of steps. But you notice that it is not a simple nucleophilic addition. You need to modify the mechanism a little bit, including a series of protonation and deprotonation. I think that was highlighted in activity 6. Yeah, you know, in activity 6, we talk about nucleophilic acyl substitution, or otherwise known as addition-elimination mechanism. And we did mention that in the process of drawing the mechanism, you need to perform some modification to the steps. Okay, and then next we have nucleophilic addition of primary and secondary amine. I think this needs no introduction. It's quite similar to what we have with the nucleophilic addition of alcohols. Yeah, but you notice that for amines, I do not really need to catalyze the reaction with acid, because number one, the lone pairs on nitrogen on amines, right, is more available to coordinate or to perform nucleophilic attack onto the carbonyl carbon. So amines are stronger nucleophile as compared to alcohols. Yeah, so because of that, then I do not need any form of I do not need to catalyze it with an acid. Yeah, so the whole process is quite similar. You notice that first it starts off with a nucleophilic attack, and then you form an alkyl site, and then after that you get what we call a hemiacetal. Okay, and then after that, the OH will be protonated. Okay, so this is a series of protonation and deprotonation. Yeah, so it doesn't go straight away to this. So I think there's an arrow missing here, which if you want to, you can add in. Okay, so my apologies. I can't really draw in the lone pairs. So there's a lone pair which is going to grab the H. Yeah, then after that, you are going to lose the H2O. Okay, and then you notice that you form this particular structure, and then the H plus will be lost, and then you form what we call an imine. Okay, so it'll be good for you to know this particular name. So this is called an imine when you have a primary amine being added, and eventually you end up with an imine with a C11N. Okay, so if you are going to use a secondary amine, what's going to happen here, if I may just expand the structure of R a little bit, right? I mean, this is just expanding R a little bit, right? Is that, okay, so maybe a better representation is R prime, because R may include a R prime CH2, so I just put R prime here. Yeah, so what's going to happen is that if I'm using a secondary amine, you notice that the R prime here cannot be easily lost. Yeah, remember that earlier on when we formed something like this, right? The H plus can be lost, but here there is no H plus to be lost. Yeah, so because of that, the H plus is being lost from the beta hydrogen. So this is the beta hydrogen. Yeah, and we are going to form something called an enamine. Yeah, and enamine is actually a very good mask form of a carbonyl compound. So I'm just going to write mask form of carbonyl. The reason why it is a mass form of carbonyl is that this particular carbon is nucleophilic. What do we mean? Okay, so when we have an electrophile here, right? You'll notice that this particular form is quite stable, so you can isolate it. Then the electrophile, right, will be added because the lone pair now can flow and form back the C double bond end, and the pi bond can now break towards the electrophile. Yeah. So the mask form of the carbonyl compound, right, I think it can be used, number one, as a stable form, and of course number two is it is a form which can potentially be used as a nucleophile. Yeah. So if you are going to ask me, how am I going to use a carbonyl compound how can I make a carbonyl compound nucleophilic? Well, you can make a carbonyl compound nucleophilic. So for example, let's say I have a propanone, for example, just a propanone, right? The hydrogen here is slightly acidic. So potentially we can use a base to deprotonate this, and I'm going to form what we call an enolate. Okay, so I can form an enolate with a negative charge here. This enolate is actually resonance stabilized, okay, because the lone pair of electrons can be delocalized into the carbonyl oxygen to give us this particular compound. Yeah, so this is known as an enolate. Yeah, so if I have an electron deficient compound here or species here, right, potentially the lone pairs can come in to reform the CO pi bond, and the pi bond is now nucleophilic, can now attack the electron deficient electrophile. And in the process, I'm able to form something like this. Yeah, so that is how the carbonyl group, in the presence of a carbonyl group, I can potentially make the alpha carbon, in this case, nucleophilic. Okay, yeah. So because of that, because I'm able to make the alpha carbon nucleophilic, then it serves as a way for me to expand my repertoire of synthetic strategies. So that means that I can potentially make a lot of new compounds out from here. Yeah. However, right, there is a drawback. The drawback is that when number one is, if I'm going to color code this, right, you'll notice that enolate has an overall negative charge, either at the oxygen or the carbon. Yeah, so that makes it highly basic as well. So on its own is not very stable, and it has to be generated in situ, meaning generated fresh. Yeah, so there is actually a mask form of the enolate, which is what we mentioned earlier on. So I think earlier on I mentioned that it's a mask form of a nucleophilic carbonyl compound. Yeah, so it's actually a mask form of the enolate, which is the enamine. Yeah, you notice that for enamine, right? I think earlier on I called this the alpha, beta. It's actually the alpha, okay? Alpha carbon. If you use the same terminology, right? Yeah. So this particular enamine, if you take note of it, is neutral. Yeah, so because it's neutral, right, you can keep it in the fridge, and it can be stored under, sometimes it can even be stored under room temperature condition. Yeah, so because of that, it has the advantage of being used preferably by scientists. But the drawback is that you have to form the enamine, and then you have to go and remove it if you don't want the enamine eventually. Yeah, and removing it, of course, you can simply perform an acidic kind of hydrolysis reaction. But it's definitely out of the scope of the curriculum to discuss all this. Of course, it can be asked in exams. Okay, so but if we are ever going to ask you in exam, then you'll be guided, so not to worry. Yep. Then next, we're going to look at the nucleophilic addition of hydrides. So essentially, this is a reduction reaction. Yeah, so you learn about two common reducing agents: lithium aluminium hydride in dry ether and sodium boron hydride in methanol. Yeah, essentially, you can represent the arrow pushing or the hydride, right, using just simply a H minus. I think in H2 we usually ask you guys to represent it with a H minus. Yeah, but for the purpose of H3, you might want to know that hydride cannot exist as H minus. So usually it is sigma bonded to a Lewis acid. Yeah, so in this case, either boron hydride or aluminum hydride. And because of that, the BH or the ALH sigma bond is highly nucleophilic. Yeah, so it can be easily added onto the carbonyl carbon and perform what we call a reduction reaction. Okay, yeah, and because the carbonyl carbon is trigonal planar in geometry, right? The hydride can approach it from the top and bottom plane with near equal probability, similar to what you understand from nucleophilic addition. Okay, however, right, I think this is a little bit this portion may be a little bit interesting, what we call asymmetric induction. Okay, so what exactly is the meaning of asymmetric induction? Asymmetric induction occurs, right, when we already have a predefined chiral center. Yeah, so this chiral center is already predefined. So this chiral center is fixed. Yeah, in terms of absolute configuration. So meaning that you cannot anyhow change from an S configuration to an R configuration. It's already fixed for you. Yeah. So when it is fixed for you, right, you do notice one thing. If I'm going to draw the Newman projection, okay, how are we going to draw a Newman projection? That means that I'm going to place my eyes here. So if I place my eyes here, right, you'll notice that the H, okay, so it's behind, so the H will be here to the left, and then the ethyl group will be to the right, and then the phenol group will be pointing below. Yeah, then I think some of you will be wondering, what about the carbonyl carbon and the oxygen? How are they going to point? Yeah, so technically they have an infinite conformation, right? Because it's a one full circle. Yeah. However, right, you will usually encounter this in exam, so they will usually guide you by telling you that, okay, the carbonyl group, right, will be orthogonal to the group with the greatest steric demand. So that means that the phenol group, okay, because we place the phenol group vertically, yeah, we place the phenol group vertically, right? So therefore, I expect the carbonyl group to be here, okay? So with a methyl over here, something like this, yeah. But this is only one way, yeah, because I can easily rotate this another 180 degrees to get the other conformation. Okay, so it's something like this and like this. Yeah. So if you are curious, if you compare between the two conformation, right, you will not know which is more stable. Okay. Yeah. But if you draw out the transition state or the intermediate, then I think you can tell quite easily. Yeah. So for here, right, the hydride usually comes from remember I told you 109.5 degrees from the CO bond. Yeah. So it approaches either from here, or you can approach from here, or either here, or oh, sorry, the other way around. Here or here. Okay. Yeah. So there are two potential approaches. Yeah. So let's just focus on one of it. Yeah. So you notice that when it approaches, okay, so maybe I'll just erase this so that it's not too messy. Okay. So you notice that in this particular approach, right, this O will now shift downwards. Okay, sorry that I use an arrow. I shouldn't be using an arrow because arrow simply means arrow pushing, right? But yeah, that's why I erase it straight away. Yeah. So when the hydride attack the carbonyl carbon, I need to push the methyl and the original carbonyl oxygen downwards. So I'm going to get something like this. So I'm just going to highlight in green, something like this. Yeah. So now the hydride is over here. You notice that this portion has steric hindrance, or what we call gauge interaction. And pretty much that's about it. Do you notice? Yeah. But for the other combination, right, maybe I'll just highlight in yellow. I'm going to end up with this. Yeah. But now my gauge interaction is between the ethyl and methyl, and as well as phenol and methyl. Yeah. So these two gauge interaction, right, means that in the transition state leading to these two intermediates, yeah, so there must be a transition state, which I'm not going to draw it out, but you will notice that in the transition state leading to this intermediate, right, the interaction will already be developing. So the gauge interaction will already be so-called present. So that means one of the transition state will be of a higher energy as compared to the other. Yeah, so that means that transition state 2 will have a higher energy than transition state 1. Yeah, so because of that, then that also means that I'm going to form this a little bit more as compared to I'm going to form the other one. Okay, so I hope, I'm not sure whether you can agree with me on that, but that is the main idea which we want to highlight to you. Yeah, so with that, in the course of a reaction, so I'm going to erase this. Yeah, so my eventual products, which I'm going to draw out, right, I'm actually going to form this OH here. Yeah, it will simply be a deprotonation fast step. Okay, so OH, this is a methyl group, and then an ethyl group here, and then a H and a phenol. Okay, and of course for the other one, it will be the same thing. It will be a OH here, a methyl, and then a H, an ethyl, a phenol, and an H here. Okay, yep. Okay, so if you look at the drawing over here, let's see how I can position the drawing. Let's see. Okay, so I think it's not drawn in the best because what they are showing here is the eclipse conformation, which I don't think they should show it. Okay, so maybe on your end you might want to redraw lah. Okay, but if I'm going to show the conformation in that particular manner, what I'm going to have will be this is a phenol, and then this is a H here, and then the ethyl group like this, so it's the same as this portion. Okay, and then after that I'm going to have my, let's say okay, the H is here. Okay, and then of course the OH is projecting away, and then the methyl group is projecting towards me. Okay, yeah, so if I'm going to just rotate this a little bit, you'll notice that it matches this. Okay, because now the H carbon and phenol are on the same plane, right? So if I just rotate this, let's say anti-clockwise a little bit, the H will now be projecting out towards me, the OH will still be pointing in, and then I'm going to put a methyl group on the same plane. Yeah, okay, so this will be the 2R3S. Okay, and then for the other one, it will look like this. The phenol is here, the ethyl group is here, the H is here, and the H is here, and then the methyl group points away, the OH towards me. Okay, and then if I'm just going to do a little bit of bond rotation outwards, okay, clockwise a little bit, then now the OH will still be pointing towards me. The H will now be away from me, and then I'm going to put a methyl group on the same plane. Okay, so this will be 2S, 3S. Yeah, so this will not be formed as much. That's why you get a 25% because of the steric demand being imposed, the gauge interaction in the transition state. Yeah, but some of you might be asking, hey, why not like 99% to 1% or even 100% of 2R and 3S? It's not possible unless the difference in activation energy is very huge. Okay, very huge, meaning more than 20 kilojoules per mole. Yeah, if it's just a little bit, then you will get a little bit of preference of one over the others. Yeah, and all these are actually not within the H3 curriculum, so you don't really need to worry too much about it. Yeah, if you're interested, you can read more about asymmetric induction, yeah, which is under the topic on asymmetric synthesis. Yep. Okay, so we're going to move on to our famous addition-elimination mechanism, which is not new to you actually. Yeah, so if you sort of recall earlier on in our activity 6, we do talk quite a bit about it. So if you want to, you could go to the video review. So please go to the video review on activity 6. Yeah. So the video review on activity 6, I talk a lot about the addition elimination reaction in some details. Yeah. Okay, so I think the notes does give you a little bit of stuff as well. Basically, why is it called addition elimination? Is because it begins with a nucleophilic addition, and then later on a small molecule is being eliminated in the process. Okay, and of course this is the ester hydrolysis using aqueous alkaline. Yeah, so we start off with OH minus, perform a nucleophilic attack delta plus, delta minus, and then in the process I will kick out the alkoxide group. Why is it that in this case I can simply kick out the alkoxide group? Because I am performing in an alkaline medium. So when you're performing the reaction in an alkaline medium, it is perfectly legitimate for you to kick out a group with a negative charge. But if you are performing the reaction in an acidic medium, then obviously water is not a good enough nucleophile, right? So I need to protonate the carbonyl oxygen in order for me to perform a nucleophilic attack onto the carbonyl carbon, and I cannot let my RO group leave as an alkoxide. It has to leave as alcohol, because in an acidic medium, alkoxide is not stable enough to leave, and it should not exist. Yeah, so that is why mechanism drawing in alkaline medium is always simpler as compared to acidic medium. You notice that in alkaline medium, right, I'm only drawing 2 steps. So this is step 1, and essentially step 2, I'm almost done. But I need to perform the final step in order to showcase to the examiner that the final product is a carboxylate anion. Yeah, okay. Then I'm going to move on to the mechanism for the hydrolysis of ester catalyzed by acid. Yeah, I think we have discussed this, especially I think this is the answer, or rather the answer to activity 6 question 14 last part. Okay, is on the formation of ester. So in our case here is the acidic hydrolysis of ester. Okay, so it begins with the protonation of the carbonyl oxygen. Okay, and the protonation of carbonyl oxygen allows a poor nucleophile such as water to attack it, and then a series of proton transfer allows me to create a good leaving group, which is R prime OH, and then now the group will leave, and then later on I'm going to deprotonate the carbonyl oxygen. Okay, so the explanation is given here. I don't think I want to go a lot more into details. Yeah, and then the final portion is the hydrolysis of amides. How is the amides being hydrolyzed? So similarly, if it's in an acidic medium, then the carbonyl oxygen will be protonated, and then the carbonyl carbon will be attacked by the nucleophilic oxygen on water, and then after that there will be a series of proton transfer. Like the NH2 will gain a H plus from here, and then later on I will reform the the CO double bond, and then I will kick out the leaving group as ammonium. Remember, acidic medium, the group cannot leave as NH2 minus, so it has to leave as a stabilized species. Yeah, and of course the ammonia group that leaves will now protonate or deprotonate the acidic proton from the carbonyl oxygen. Yeah, to give us NH4 plus, which is the ammonium. Okay, so this is a similar mechanism. You can draw it yourself if you want to. I think it will be good to practice addition-elimination mechanism for H3 because they are of vital importance, often tested. Okay, how do we propose reasonable mechanism? I think you can read about it on your own. You can read this portion. I think we have talked about it very often. I think earlier on we did share with you some of the mechanism that is not reasonable and is unlikely. So in this case, it is almost impossible for me to perform just a nucleophilic attack on the carbon and then allowing the ethoxide group to leave, because number 1 is a very poor leaving group. Okay, and of course number 2 is the carbon obviously is a poorer nucleophile as compared to ethoxides. Okay, so there are many points you need to consider when you propose a reasonable mechanism. It cannot be summarized. There is no generic simplified rules. Yeah, so I really cannot share with you what are the simple rules which you can follow. But largely is, I think in my review to activity 6, I did mention one little things known as the principle of microscopic reversibility. Yeah, so that particular principle tells you that whatever forward reaction you propose, right, there must also be a similar backward reaction, because all reactions are somewhat reversible if you look at it in the greater scheme of things in an energy profile diagram. Yeah, okay, so I just urge you to, I mean, a good way to improve on mechanism drawing, of course, is to work with more examples lah. Yeah, so if you are able to work with more examples, then I think you will be a lot more familiar with mechanism drawing, and then usually that will be okay. Okay, so I think I will just leave you all to read all these portions, and usually for novel mechanism for H3, you'll be guided with some words or paragraphs to teach you how to perform the mechanism drawing. Yeah, so in that sense, you do not need to worry too much about it lah. Okay, yeah. So if you are in any doubts, do clarify with your tutors so that we can help you in every way we can. Because we do know that mechanism drawing can be very daunting, and it represents some of the most difficult parts under the H3 curriculum. In fact, even in university, students have great problem with mechanism drawing. Okay, so with that, we'll come to the end of the lecture. Before we end, we're just going to work on exercise 5. For exercise 5A, you were given an alkene and the inorganic reagent HCl. You were not given or you were not told whether HCl is aqueous or whether it's solvated in some organic solvents. So it doesn't really matter here. I mean, at the end of the day, of course, if you were told, then it matters and you can make a better prediction of the mechanism. But in this case, you were not told. Yeah, but the clue you were given is that it goes through a carbocation, a secondary carbocation. Yeah, so from here, what you can postulate would be perhaps you will first draw out an electrophilic addition involving HCl. Yeah, so you know that HCl has a bond polarity. Yeah, so H will take on a partial positive charge, so that will be the electron deficient sites. Yeah, so let us try to draw the electrophilic addition product first. So first, we're going to draw out the carbocation. Yeah, so essentially this is the carbocation which was given to us, so with a plus charge over here. Yeah, but do take note that the chloride that is being given out, right, if it attacks at this particular secondary carbocation, we will not be able to get the products given to us. Yeah, so you know that it is unlikely that for us to get the tertiary chloroalkane, the chloride will attack the secondary carbocation. Yeah, so that means that we have to modify the mechanism slightly, or maybe it involves some form of shift, alkyl shift or hydride shift, which you learned in the earlier parts of this particular set of notes. Yeah, so maybe what we can propose is, okay, so you know that I must generate a tertiary carbocation. So over here, maybe we can postulate that there is a tertiary carbocation where the chloride can perform a nucleophilic attack at the electron deficient sites, and I'm going to get the tertiary chloroalkane. Yeah, so in order for us to produce this, there must be some form of shift. So you could, maybe if you remember from the earlier parts, it should be a hydride shift. Yeah, so this particular H will then shift towards this secondary carbocation, and in the process it produced the tertiary carbocation. Yeah, and since we were given the clue that it goes through via this secondary carbocation, then a hydride shift is likely to have taken place in one of the steps. Yep. Okay, so that will be the end of A. Next, we're going to move on to B. Yeah, B does look a little bit familiar, because if you look at it, in the course of the reaction, I end up with a ketone and a diol. So if I'm going to just scroll back, I'm not sure whether it resembles the ketal, which we were discussing earlier on. Yeah, correct. So this is the ketal which we were discussing earlier on, where the original carbonyl carbon is bonded to 2 oxygen. And in fact, those 2 bonds are part of the ether bonds. So ether is this particular functional group where we have an R, and then we have an O, and then another R. Okay, yeah, so I think we can go straight to page 52. Okay, so over here, there are 2 CO. In fact, there are 2 ether. Yeah, and you know that they are bonded to the same carbon. So to some extent, you know that this is a ketal. Okay, yeah, so because of that, remember earlier on, maybe in activity 6, can't exactly remember, I talked about the principle of microscopic reversibility, right? Yeah, so perhaps the first step, you do expect some form of protonation, because we have HBr catalytic. Okay, so in this case, delta plus, delta minus. Yeah, so the lone pairs of electrons will then attack the electron deficient hydrogen, and then the bromide will leave. Yeah, so in this case, I'm going to generate the conjugate acid. Okay, so the conjugate acid will look something like this. So with an O here, and then like this, with a H, and then a plus. Yep, and then a 6-membered ring. Yep, and how is this going to continue? Yeah, so it's going to continue because if you recall what we did earlier on, right, we need to generate a carbonyl CO group. Yeah, so the carbonyl is likely to be generated where the lone pairs of electron will be pushed in, and then in the process neutralize the positive charge at the oxygen. Yeah, so because of that, I'm going to draw out the product. So it's going to look something like this with a double bond O and then an OH, and then this double O will have, the oxygen will have a +1 formal charge. Yeah, so it looks like this particular structure, but it's not exactly this structure yet. Quite similar, but not quite this particular structure. Yeah, so how do we reach this particular structure? Yeah, so you notice that the only difference is that that you form a CC pi bond here instead of a CO pi bond. Yeah, so that means that some form of tautomerization will have occurred. Yeah, so tautomerization was introduced to you in activity 2. Yeah, so let us try to draw the tautomerization product. So in this case, like this and like this. Okay, so because of that, I'm going to form an alkene-like structure like this. Okay, yeah, this particular structure is known as an enol. Okay, remember earlier on we talked about enolates. Yeah, enolates is when the oxygen takes on a negative charge, and then the alpha carbon is a nucleophilic carbon. Yeah, so enol is the same thing, except that the oxygen do not take on a negative charge. Yeah, but it still has the nucleophilic lone pair where it can flow directly into the carbonyl carbon, and then the CC pi bond will become nucleophilic and it will attack any electron deficient sites. And this is exactly what happens here. Yeah, so if you look at what happens here, we have bromine and HBr catalytic. Yeah, and then you notice that one of the bromine is now added to the alpha carbon. Yeah, so you could probably from here postulate that, all right, so now the lone pairs of electrons can then come in, and then it will then be added to the bromines. Okay, so when some form of electrophilic addition. Yeah, so similar to what you normally do with the electrophilic addition of alkene to bromine, or bromine to alkene in that sense. Yeah, you do not need to show the cyclic bromonium. I think earlier on we showed you the cyclic bromonium. Yeah, in this case you do not really need to show it for a very simple reason, because cyclic bromonium is usually applicable for a pure alkene. In this case is more of an enol, yeah, where the CC pi bond is highly nucleophilic, so the cyclic bromonium is not likely to have taken place. But again, all these things are postulate. We really don't know. Okay, so after that, we are going to get a CO double bond here, and then we have a Br. Okay, and then we're just going to get the OH in here with a plus charge. Okay, then in that case, how do we get back this particular ketal? Yeah, so that will be straightforward. Okay, so again, this is the carbonyl carbon. And because with a +1 formal charge at the oxygen, now nucleophilic attack will take place. So you are going to get an internal nucleophilic addition, and then of course eventually you're going to end up with this again, and then with an O here, and then an O here with a H. Now we have a +1 formal charge, and then the H will be lost as a H+, so minus H+, and then we're going to get the product. Okay, right. We are not quite here yet. We haven't reached the ketone yet. So let me circle this portion. Yeah. So we have jumpstart to give us this particular product where the ketal obtain a Br, or one of the H at the alpha carbon is now substituted with a bromine. Yeah, so we have moved away from our original intention, but it doesn't really matter because we can actually continue from here. So we're going to continue from this particular intermediates, okay, in order for us to get the cyclohexanone. Okay, so I'm going to just draw in the space below. Okay, so we are going to have this. Alright, and then with a plus charge, and then with a OH. Okay, and remember that the system is likely to again contain H2O. Yeah, so because it contains H2O, we're going to allow the nucleophilic attack to take place by the water, and then at the carbonyl light oxygen, carbonyl light carbon, and then nucleophilic addition will then take place in a relatively ordinary fashion. So we're going to end up with what we call earlier on as the hemiketal. Okay, and then the same logic will take place. The H plus, okay, will then protonate this particular etheric oxygen. Okay, and then in the process, it will gain a +1 formal charge. Okay, and then the lone pairs of electrons will then come in to form the carbonyl oxygen and then kick out the diol. Okay, so in the process, the diol will be kicked out. So I'm going to draw the diol here. Okay, kick out, and then I will get a carbonyl oxygen with a +1 formal charge. So this is a cyclohexane, the conjugate acid of cyclohexanone, and then the OH bond will now hydrolytically cleave and then to regenerate cyclohexanone. Okay, so that's how the whole mechanism works for parts B. Okay, I hope you are okay with this mechanism. Okay, and then part C onwards, C and D is actually a little bit more complicated, so I will need a little bit more time to discuss. Okay, but of course you are given a bit of hints here. So the first step involves the protonation of formaldehyde to give the conjugate acids of formaldehyde. Okay, you may be wondering where is formaldehyde. So this is actually formaldehyde. Yeah, and of course you were told that the first step involved the protonation. So since they told you it involved protonation, so you don't do much, just protonate, and then I'm going to get the conjugate acid of formaldehyde. Okay, I'm just going to do it first, and then the next thing is remember what I often mention. It's always good to number your carbon. Okay, so I'm going to number the key carbon, so that will be 1, 2 over here, and then 1, 2, and then 3, 4, and 5. Okay, so you notice that because of the way I number the carbon, something must be added so that I'm able to link up this particular ketone here. This is known as acetophenone. Okay, acetophenone. Okay, it's quite a popular structure where we often use it to elongate the molecules and for other purposes. So you're going to see this quite often. Okay, yeah, so what I'm going to propose here is we're going to take it slowly, because let us just use the hints to help us propose the mechanism. So the conjugate acid of formaldehyde reacts with dimethylamine to give this particular weird looking molecule. So if I'm going to number the carbon, this will be 4, 5, and then this is 3, right? Yeah, so that means that my dimethylamine, right, is going to perform the nucleophilic attack on the carbonyl carbon at formaldehyde and the conjugate acid of formaldehyde. Okay, so I'm going to draw this out. I'm going to draw out the dimethylamine, okay, like this, and then with the lone pair, and then nucleophilic attack at carbon number 3, and then pi bond breaks. So this is essentially a nucleophilic addition kind of reaction. Okay, so in the process, I'm just going to draw in blue. I'm going to end up with a structure that looks like this, with a OH, and then a H, and a H, and then a sigma bond N, and then this is the conjugate acid with a plus charge, and then with 2 other bonds, which is the methyl groups 4 and 5, and this is 3. Okay, yeah, in order for me to get the NC double bond, right, so it is likely that there is some form of intramolecular proton transfer. Yeah, so this particular proton can be transferred to the primary alcohol. Okay, like this. Yeah, so generally this kind of transfer is it can take place quite often, because the reaction technically they are all in equilibrium. Okay, so I'm going to draw out this, and then yeah, so I'm going to number the carbon again. So there's 3, and then 4, 5. Yeah, and then now my nitrogen takes on a positive formal charge. So definitely I'm going to kick out, so some form of addition-elimination. So I'm going to form the CN pi bond, and then I'm going to kick out the H2O as water. Okay, so eventually I'm going to end up with something like this, with a double bond, and then H, and then of course N here, and then yeah, so I'm going to get this particular species. Okay, it's quite an interesting species, and this species is often used in a reaction like this in order to elongate the chain. Yeah, so now acetophenol will get protonated to give the enol. Yeah, so I think this will not come as a surprise, because formaldehyde can be protonated. So of course acetophenol can also be protonated as well. So I'm going to protonate the acetophenol. Okay, so acetophenol looks like this. And then I'm going to show the protonation. Yeah, it'll always be good to showcase arrow pushing. Do not take shortcuts. Yeah, because if you try taking shortcut in the beginning of your learning, then I think in the future you will not draw proper mechanism lah. So that's our belief, that when we often teach you mechanism drawing at the start, we just want to ensure that you do not take shortcuts. Okay, so from here I'm going to get the enol. Okay, so the enol will look like this. Yeah, and now all stars are aligned because it's carbon 1 and carbon 2. Yeah, so of course enol generates what we call a nucleophilic carbon over here at carbon number 2, and the weird looking structure with the, which looks like, I mean, with a quaternary nitrogen, okay, is electron deficient at this carbon number 3. Yeah, so now all stars are aligned. So now what's going to happen is that the lone pair on the oxygen, okay, will now flow in. And remember, enol is nucleophilic at one of the carbon, that is the alpha carbon. So the pi bond will now act at carbon number 3, and then the pi bond will now break towards the nitrogen to neutralize the charge. Okay, and in the process, I'm going to get a structure which looks very similar to my products. Okay, so I'm going to have this with a plus charge. Okay, that's 1, 2, and then 3, and then nitrogen here. Okay, so I'm just going to number the carbon 1, 2, 3, and then 4, 5. Yeah, we are almost done. Okay, so the final step is simply to neutralize the positive charge at the carbonyl oxygen, where the O bond will break heterolytically, and then I will lose a H+, and in the process I'm going to get a product which I desire. Okay, so some of you might be wondering, all this bond forming, bond breaking, right, how does it actually take place? And all this H+, right, it's lost to which species? Okay, that is a very valid question, which along the way I think I didn't answer. But if you look at dimethylamine, right, it can also serve as the base to deprotonate all these H's. Yeah, so in some sense, if you want to draw a slightly more accurate mechanism, actually dimethylamine should probably be the species to abstract the H, and you shouldn't write it as a minus H+. And then this particular H+, if you want to be a little bit more strict, right, it should actually comes from the conjugate acid of dimethylamine. Okay, I think this will be a little bit more accurate, so it should be like this. Yeah, but in most cases, when we give you a novel mechanism with not much assistance, yeah, I think if you can draw what I have drawn for you earlier on without the due consideration that dimethylamine could be the base which abstract the H+, I think that should be fine without much clue given to you. Yeah, but of course, in most cases, we do give you some clues to tell you that, you know, by considering the nature of dimethylamine suggests how can the proton be removed, etc., etc. So yeah, so clues will be given where necessary. Okay, so next we're going to move on to part D. Yeah, so part D again, quite similar. So now we have benzoic acid. It's written as catalytic, so it's probably the one which contribute H+. Yeah, so it's a source of H+. Then we have this cyclic molecule which is secondary amine, so it's probably used to remove any protons. Okay, then we have an interesting looking structure here. We have an interesting looking structures over here. Yeah, so if you notice, there are two electron withdrawing CO group bonded to a CH2. So it does tell you that the CH2 is likely to be quite acidic. Yeah, so it can easily be deprotonated to give the corresponding enol. Yeah, and potentially the carbon flanked by the 2 electron withdrawing group can be made nucleophilic. Yeah, so all this will kind of make sense, because if we were to number the carbon, we just number this as carbon number 1, so this is likely to be the nucleophilic carbon, and then carbon number 2 is likely to be the electron deficient carbon, which makes sense because aldehyde is electron deficient at the carbonyl carbon. But of course, in the presence of benzoic acid, I think the first thing we might want to do is to protonate the carbonyl oxygen. Yeah. Okay, so the first thing we want to do here is to protonate the carbonyl oxygen using benzoic acids as the carboxylic acids. Okay, so we're going to just draw this in like this. Okay, and then in the process, we are going to get the protonated form of benzaldehydes. And in this sense, it makes the carbonyl carbon more electron deficient. Yeah, and then you might be wondering, in this case, what is the role of this molecule then? Yeah, again, I mentioned already, carbon number 1 is the nucleophilic carbon. So your role is to form the relevant enol. So I'm going to do it now. Okay, so I'm just going to draw out ETO. Okay, so O, and then O and OET. Okay, and not to forget, in order to generate the relevant enol, right, the carbonyl carbon needs to be protonated, because if not, we are going to produce an enolate, which it's not likely to be possible in the presence of carboxylic acid. Yeah, of course, the medium, we are not very sure, is it acidic, is it alkaline? Yeah, but in most cases, we probably just want to keep the system neutral, at least for our case here. Okay, so maybe the first thing you might want to do is protonate the carbonyl oxygen first using benzoic acids. Okay, so we're going to do it similarly to what we have done earlier on. So I'm going to protonate benzoic acid, or rather deprotonate benzoic acids. Yeah, so in the process, I'm going to generate the protonated form, or the conjugate acid of this diester. Okay, and of course, in the process, one of the H will be lost. Okay, so it will be grabbed by this particular secondary amine. Remember, we mentioned that where possible, find a source of a source of base to deprotonate. Okay, so I'm going to form the enol. Okay, so once the enol is formed, then all stars will be aligned, because once the enol is formed, it will look like this. Yeah, I'm just going to draw it out properly. Okay, OH and then OET. Yeah, so again, as we mentioned earlier on, the enol, the carbon, okay, flanked by the 2 carbonyl group will be the nucleophilic carbon, and the carbon bonded to benzaldehyde will be the electron deficient carbons. Yeah, so when this happens, then we're just going to push the arrows, and then the pi bond will now attack the carbonyl carbon, and then the CO pi bond will now break towards the oxygen to neutralize the charge. Okay, so I'm just going to draw this out quite quickly. So what's going to happen is I'm going to draw the phenyl ring, and then the OH here. Okay, and then of course I'm just going to draw out, so this is carbon 2, so this is carbon number 1, and then I'm going to have a OH plus here, and then OET. Okay, and then of course the carbonyl group with a OET. Okay, right, so what's going to happen next would be there should be an intramolecular proton transfer. Yeah, why must there be an intramolecular proton transfer? Because eventually I'm going to form a CC pi bond between carbon 1 and 2. Yeah, so that means that some form of elimination or dehydration must have taken place. Yeah, so for the dehydration to take place, now the lone pairs of electrons on the secondary alcohol will grab the H from the carbonyl oxygen, and then the OH sigma bond will now break heterolytically towards the oxygen, and then along the way I'm going to get this particular protonated form of the alcohol, so OH2 with a plus charge. Okay, and then I'm just going to continue to draw the structures like this. OET, and then double bond O and OET. Okay, so some form of elimination is likely to have taken place. Okay, and then you might have, most people will have predicted some form of a E2 reaction. So what do we mean by E2? So therefore, this particular secondary amine, okay, the lone pairs of electrons of nitrogen will grab the H here. Okay, so there's a H here, and okay, so okay, let me draw it out a little bit more clearly. Yeah, so there's a H here, so the lone pair will grab the H, and then the CH pi bond will now break, and then I will eliminate the water, and then eventually I should be able to get the product. Okay, so if you draw it this way, it's perfectly fine. There is nothing wrong with the way you have drawn it. Okay, but perhaps if you read out a little bit further, right, because we have two electron withdrawing group, some of you might have read up something called the first order elimination conjugate base, what we call E1CB. Okay, so how does this work? Just going to show you. Okay, so because we have two electron withdrawing group, so it is likely that some form of the carbonyl oxygen can be a potential electron sink. Okay, so because of that, this particular group, secondary amine, right, can abstract the H, and then now the CH bond, instead of straight away do a E2 like mechanism, right, it will be pushed towards the carbonyl oxygen. Okay, I know you are going to argue that, oh, but now I will generate a minus charge. Yes, but actually the minus charge is resonance stabilized if you take a look at it quite closely. Yeah, so in this case it's actually so-called okay lah. I mean, yeah, but we cannot say for sure the mechanism, because in most cases we all these things is unknown until we perform an experiment. Okay, so if you propose something like a E1CB kind of mechanism, it's actually okay. Yeah, but usually E1CB kind of mechanism, right, works more for a strong base. So if you use a strong base, then it might work, and especially the case where you perform the reaction in an acidic medium. Yeah, so in our case here, if you propose a E1CB, I would say that it's not so likely. So maybe I just put a remark here. So this is not so likely. Yeah. But we can't say for sure that it will not take place lah. Yeah. So the one we have predicted here, which is more like a E2 kind of mechanism, it is more likely. Yeah. But at the end of the day, we are really not sure until you have done kinetic studies. Okay. Yeah. So with that, we are pretty much done in going through all the 4 parts to exercise 5. So I hope you find the review useful in your learning. Then do pay attention to your mechanism drawing. I know we introduced mechanism at the very beginning of H3. Some of you might be a bit uncomfortable, but we rather do that than to introduce you to mechanism later on where you are going to get lost anyway, or you're going to feel lost anyway. Yeah, so between now to your prelim or A-level exams, take the opportunity to practice, and then most of you should be fine when you reach A-levels. Okay, so all the best in your mechanism drawing. With that, we'll see you in the next video.